Mid-February 1943. Kummersdorf Proving Ground, Brandenburg, Germany. The captured M4A1 Sherman tank, designated Versuchfahrzeug 259, sat motionless in the morning cold, its transmission housing opened like a dissected specimen. Oberingenieur Klaus Reinhardt crouched beside the exposed gearbox, notebook in hand, studying the arrangement of gears and synchronizer rings that had brought him and his colleagues to this moment of profound technical unease. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The tank had arrived 3 weeks earlier, shipped from Tunisia after capture at the Battle of Sidi Bouzid. Serial number USA 3067641, built by Lima Locomotive Works. Every component tagged, photographed, measured. The German Army Weapons Office had issued explicit instructions. Understand this machine. Determine how the Americans achieved what German industry had failed to accomplish. Discover why their tanks kept running when German panzers broke down. Reinhardt's gloved fingers traced the helical-cut synchronizer rings in 2nd through 5th gears. The design was elegant in its simplicity. No double clutching required. No careful rev matching demanded. An ordinary soldier with basic automotive knowledge could shift these gears as easily as driving a civilian automobile. The implications were staggering and deeply troubling for a man who had spent his entire career designing German tank transmissions that demanded specialist operators and constant expert attention. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The mathematical reality was inescapable. American automotive engineering had achieved operational reliability that German precision manufacturing could not match. This single transmission, unremarkable by American standards, represented decades of civilian automotive industry experience that Germany fundamentally lacked. The synchronized manual gearbox, standard in American cars since the 1930s, had been adapted to military service with devastating effectiveness. German tanks, built by craftsmen using traditional methods, could not compete with mass-produced machinery designed for conscript operators and field maintenance by mechanics with minimal training. Spring 1943. German tank production facilities scattered across the Reich were approaching maximum output under Albert Speer's rationalization programs. Factories in Berlin, Kassel, Nuremberg, and occupied Czechoslovakia produced Panthers, Tigers, and Panzer IVs, at rates that would have seemed impossible in 1939. Yet commanders at the front sent increasingly urgent reports about mechanical failures that eliminated more tanks than enemy action. Transmissions failed. Final drives broke. Engines overheated. The German tank force, despite tactical superiority and crew skill, was dying through attrition caused by automotive inadequacy rather than combat losses. The problem was fundamental and structural. German tank design philosophy prioritized theoretical performance specifications over practical operational reliability. Engineers calculated tolerances to achieve maximum efficiency, creating transmissions that performed brilliantly under ideal conditions but failed catastrophically under field stress. Straight-cut gears provided optimal power transmission but required precise synchronization and careful operation. Unsynchronized transmissions demanded skilled double-clutching and rev matching that ordinary conscripts struggled to master. Every system assumed highly trained specialists would operate and maintain the vehicles using specialized tools and extensive technical knowledge. American engineers, by contrast, designed for the reality of mechanized warfare. Conscript. Soldiers would operate these machines. Field mechanics with automotive training but no specialist expertise would maintain them. Combat conditions would subject every component to stress beyond design specifications. The transmission must function reliably regardless of operator skill. Gears must shift smoothly without precise technique. Components must tolerate abuse and continue functioning. The entire powertrain philosophy accepted that ordinary people would use these tanks under terrible conditions, and the machinery must accommodate human limitations rather than demanding perfection. The Sherman's transmission embodied this pragmatic design philosophy in every component. 5 forward gears plus 1 reverse. Synchronization in gears 2 through 5 eliminated double clutching. First gear and reverse, used only at low speeds, required no synchronization. The shifter pattern was identical to civilian automobiles, requiring no specialized training. Gear ratios were carefully selected to provide adequate performance across all operating conditions, without demanding perfect technique. The entire system could be operated by anyone who could drive a standard American car. Reinhardt had spent 3 days studying the transmission's internal components before reaching conclusions he found professionally embarrassing. The synchronizer rings used friction material to match gear speeds before engagement, eliminating the need for driver skill in timing clutch operations. The design was mechanically sophisticated yet operationally simple. German transmissions, lacking synchronization, required drivers to depress the clutch, shift to neutral, release the clutch, rev, or let the engine slow to match gear speeds, depress the clutch again, and complete the shift. This double clutching technique demanded training, practice, and concentration. Errors damaged gears and could destroy the transmission. Under combat stress, even experienced drivers made mistakes. The American system made such errors nearly impossible. A driver shifted like operating any civilian vehicle. Depress clutch, move shifter, release clutch. The synchronizers handled the rest. This simplification had profound operational implications. German panzer divisions required weeks training drivers in double clutching technique. American armor units could deploy drivers with minimal additional training beyond basic automotive skills. German crews worried constantly about transmission damage from improper shifting. American crews simply drove their tanks without concern for technique. The difference between requiring specialist skills and accepting ordinary competence determined whether armored units could be rapidly expanded or remained limited by available trained personnel. June 1943. Heeresversuchsstelle Kummersdorf conducted comprehensive automotive trials, comparing the captured Sherman against German tank designs. Test engineers drove vehicles through obstacle courses designed to stress every mechanical system. They measured fuel consumption, monitored engine temperatures, recorded transmission behavior under varying loads and terrain conditions. After each trial, they disassembled components to examine wear patterns, looking for signs of stress, inadequate lubrication, or design weaknesses that would cause premature failure. The Sherman performed adequately in every category and excelled in the one metric German tanks consistently failed: operational endurance without maintenance intervention. The powertrain continued functioning through conditions that would have disabled German vehicles. The transmission shifted smoothly through thousands of cycles without adjustment or repair. The final drives maintained consistent performance, despite sustained operation under load. Every system reflected design margins that exceeded immediate requirements by substantial factors, providing reliability that seemed wasteful by German engineering standards but proved essential under combat conditions. German test engineers documented operational ranges exceeding 2,000 kilometers before requiring major maintenance. German Panthers, by comparison, barely achieved 500 kilometers before transmission or final drive failures forced them from service. The disparity was not marginal. It represented fundamental differences in design philosophy and manufacturing capability. Sherman transmissions used helical cut gears and generous clearances that tolerated manufacturing variations and operational stress. Panther transmissions employed straight-cut gears with tight tolerances that provided optimal theoretical performance but failed under sustained use. The American approach sacrificed engineering elegance for operational reliability. The German approach pursued technical perfection at the cost of practical functionality. The synchronization system particularly impressed German engineers examining the Sherman's powertrain. The synchronizer rings were brass, a material choice that seemed extravagant given Germany's chronic shortage of non-ferrous metals. But the brass rings provided the exact friction characteristics needed for smooth gear engagement. They wore gradually and predictably, requiring replacement only after extensive use. The design accepted that components would wear and need replacement, but ensured the transmission functioned reliably until that replacement became necessary. German transmissions, lacking synchronization, subjected gears to impact loading during shifts. This caused stress concentrations and accelerated wear, particularly in third gear, which Panther drivers learned to avoid using because it failed so frequently. By summer 1943, the pattern had become impossible to ignore through field reports accumulating from every front. Panther tanks required strict operational restrictions to prevent mechanical failures. Drivers received explicit instructions not to change gears frequently, as excessive shifting damaged the transmission. Third gear in particular broke often enough that field manuals warned against its use except when absolutely necessary. Panthers could not turn while backing up as this would destroy the transmission. Pivot turns were only possible when ground resistance was equal on both tracks, severely limiting tactical flexibility. Foreign objects entering the running gear could jam the drive sprocket, requiring hours of maintenance to clear. These problems existed despite Panthers being built in dedicated tank factories by skilled workers using the best available materials Germany could provide. Henschel, Mann, and Daimler-Benz employed thousands of craftsmen trained in precision manufacturing. Production facilities used the finest machine tools German industry could supply, yet the vehicles these factories produced required constant expert attention and failed at rates that made operational planning nearly impossible. Unit commanders never knew whether their Panthers would complete missions before mechanical failure immobilized them. Maintenance personnel struggled to keep any significant percentage of vehicles operational. The Wehrmacht was losing the war of automotive reliability before the first shot was fired in most engagements. The Sherman, by contrast, had been designed by automotive engineers at General Motors, Ford, and Chrysler, applying mass production principles they had developed over decades of civilian vehicle manufacturing. The tank incorporated commercial automotive components wherever possible, leveraging existing supply chains and manufacturing expertise. The transmission came from multiple manufacturers, including Caterpillar Tractor, Buick, and Ford Motor Company, all building to identical specifications with fully interchangeable parts that could be mixed freely without adjustment. This standardization, routine in American automotive industry, remained largely theoretical in German tank production, where each manufacturer introduced subtle variations that prevented true parts interchangeability. Additional captured Shermans arrived at Kummersdorf through 1943 and 1944, including tanks taken from British units in Italy and Soviet forces on the Eastern Front. Each captured vehicle underwent similar testing protocols, building a comprehensive database of American tank capabilities across different variants and production periods. Engineers examined transmissions from M4A1 tanks with Continental radial engines, M4A2 tanks with General Motors twin diesel engines, and M4A3 tanks with Ford GAA V8 engines. Every variant demonstrated the same fundamental characteristic: excellent automotive reliability, derived from sound engineering principles and quality manufacturing processes. The consistency across variants impressed German engineers, who were accustomed to significant quality variations between different manufacturers, producing nominally identical vehicles. American standardization ensured that components from any manufacturer fit any vehicle without modification. A Sherman transmission built by Caterpillar in Illinois functioned identically to one built by Ford in Michigan. Parts were truly interchangeable, not merely theoretically compatible. This level of manufacturing precision and quality control exceeded what German industry achieved even with its vaunted reputation for engineering excellence and craftsmanship. October 1943 brought expanded testing programs, as Wehrmacht forces retreated across multiple fronts and additional captured equipment reached Kummersdorf. Engineers conducted reliability trials specifically designed to replicate combat conditions. They drove Shermans through hundreds of kilometers of cross-country movement, recording every mechanical incident, maintenance requirement, and component failure. They compared these results with field reports from Panther and Tiger units operating on the Eastern and Italian fronts. The numbers told an unambiguous story about comparative reliability. Panther operational readiness averaged below 40% through most of 1943, with some units reporting catastrophic rates as low as 20 to 25%. Individual Panther battalions documented periods when fewer than 1 in 5 tanks were actually capable of combat operations. By comparison, Sherman tanks maintained substantially higher operational availability across all theaters. The difference was not subtle. It was the difference between having an effective armored force and having an impressive collection of broken vehicles awaiting repair. Specific data from German field reports documented Panther reliability problems in devastating detail. In July 1943, during Operation Citadel at Kursk, Panthers achieved only 16% operational readiness with mechanical failures, eliminating more tanks than enemy action. By December 1943, readiness had improved to only 37%. February 1944 reports showed 37% operational. April 1944 reached 50% operational. May 1944 finally achieved 78%. These figures represented the percentage of Panthers that were actually capable of combat operations on any given day, with the remainder broken down, awaiting parts or undergoing repairs. The progression showed gradual improvement as design flaws were addressed. But even the best Panther readiness rates never matched what Shermans achieved from initial production. The American tanks simply worked. They started when needed. They drove when ordered. They continued functioning through conditions that disabled German vehicles. This reliability advantage translated directly to combat effectiveness. A Sherman arriving at the battlefield with an operational gun was infinitely more valuable than a Panther with superior firepower broken down, 20 kilometers behind the lines. December 1943 brought the pattern to undeniable clarity through accumulation of data that could no longer be dismissed or explained away. Engine lifespan for the Sherman diesel variant exceeded 3,000 kilometers under proper maintenance. Panther engine lifespan barely reached 1,000 kilometers, even after improvements addressed the worst early problems. German reports from March 1944 documented that improved Panther engines achieved service life of 700 to 1,000 kilometers, presented as a success. This improvement merely brought Panther engines to roughly 1/3 of Sherman diesel capability. Sherman transmissions required minimal maintenance between overhauls with synchronized gears that made driver error less likely to cause damage. Panther transmissions demanded constant attention and frequent repair, with third gear failures so common that drivers learned to skip from second to fourth gear to avoid using the problematic ratio. Sherman final drives operated reliably under conditions that routinely destroyed Panther final drives within 100 to 200 kilometers of operation. The comparison was not between good and better, it was between functional and catastrophically inadequate. Field reports from German units using captured Shermans reinforced the Kummersdorf testing data with real-world operational experience. German mechanized units, desperate for reliable vehicles as their own tank inventory degraded, eagerly employed any captured American tanks they could obtain intact. Unlike Soviet T-34 tanks, which Germans modified extensively before use, Shermans entered German service without changes. They did not require modification because they worked correctly as designed, with no fundamental flaws that needed correction. German tank crews, who had experienced multiple mechanical failures in their own vehicles, found the Sherman's reliability remarkable and frequently commented on it in letters and reports. Reports from Panzer regiments noted that Sherman operators could focus on tactical considerations and combat effectiveness, while Panther and Tiger crews constantly worried about reaching the battlefield without breakdown or completing missions before mechanical failure immobilized their vehicles. This psychological burden was itself a combat disadvantage. Crews who trusted their vehicles fought more effectively than crews perpetually concerned about mechanical failure. The 10th SS Panzer Division captured 12 M4A3 Shermans at Herlisheim in January 1945 during Operation Nordwind. These tanks had belonged to the American 43rd Tank Battalion and were captured intact when their crews abandoned them during the German assault. The 12 Shermans were formed into the 13th Company of the 10th SS Panzer Regiment and served in combat operations for the remainder of the war. These tanks served as reconnaissance vehicles and mobile reserves, roles that required sustained movement without maintenance stops and reliable mechanical performance. German commanders recognized what Kummersdorf testing had proven years earlier. American tanks could be relied upon to function when needed. This dependability, more than firepower or armor protection, determined tactical utility in the final months of the war. A Sherman arriving at the battlefield with an operational gun was infinitely more valuable than a Panther, with superior firepower broken down 20 kilometers behind the lines awaiting transmission replacement. January 1944 brought expanded testing programs as Wehrmacht forces retreated across multiple fronts, and the full implications of American automotive superiority became impossible to deny. Engineers at Kummersdorf prepared comprehensive internal reports documenting their findings for circulation through Wehrmacht technical branches and the Armaments Ministry. These documents, intended for senior officers and ministry officials, painted a sobering picture of comparative capabilities that many recipients found difficult to accept. The Sherman demonstrated American automotive engineering maturity that Germany fundamentally lacked despite its theoretical knowledge and scientific expertise. Mass production techniques allowed tolerances that would be considered sloppy in German precision manufacturing, yet resulted in more reliable vehicles that functioned better under field conditions. Interchangeable parts meant field repairs could be accomplished with basic tools and minimal specialized training, while German vehicles required factory-level precision and specialized equipment for many repairs. The entire design philosophy prioritized keeping vehicles operational rather than achieving theoretical performance maximums that looked impressive in specifications but could not be maintained in combat. Internal German engineering assessments documented observations about American industrial advantages that went beyond simple production numbers. American automotive engineering reflected decades of civilian industry experience that Germany had never developed at comparable scale. Before the war, the United States had widespread automobile ownership with vehicles commonplace among ordinary citizens across all economic classes. Germany had far more limited civilian automotive experience, with cars remaining luxury items for the wealthy and party elite. The Volkswagen program promised to German workers since 1934 had delivered fewer than 1,000 civilian vehicles by 1939. This vast difference in automotive industry maturity translated directly into tank design philosophy. Americans built tanks that mechanics with civilian automotive training could maintain using skills they already possessed. Germans built tanks that required specialist training and constant expert attention from personnel with years of specific military technical education. The comparison extended beyond individual vehicles to entire military organizations. American armored divisions could be rapidly expanded by drafting civilian mechanics who already understood automotive systems. German panzer divisions remained limited by available trained specialists who required months or years of education before they could effectively maintain complex German vehicles. The transmission comparison became symbolic of broader industrial disparities that determined the war's outcome. Germany entered World War II with technical advantages in many weapons systems, possessing scientific knowledge and engineering expertise that exceeded most opponents. However, Germany lacked the industrial depth and manufacturing sophistication to maintain those advantages through sustained mass production while simultaneously fighting enemies on multiple fronts. The United States entered the war with weapons that were less technically sophisticated in many respects, but possessed industrial capacity to manufacture them in overwhelming quantities while continuously improving quality, reliability, and performance based on combat feedback. By spring 1944, Wehrmacht units on all fronts reported increasing mechanical problems as manufacturing quality degraded and spare parts became increasingly scarce. Panthers required transport by rail for movements exceeding 100 kilometers because their final drives could not survive sustained road marches. Field commands issued explicit orders restricting Panther movement to preserve the vehicles for actual combat rather than losing them to mechanical failure during approach marches. The Berger Panther recovery vehicle, built on a Panther chassis to recover disabled Panthers, shared the same reliability problems as the tank it was supposed to recover. German commanders faced the grim reality where mechanical failures eliminated more tanks than enemy action, with some units reporting that 70% of tank losses were due to breakdowns rather than combat damage. Meanwhile, Sherman production continued at unprecedented rates that German industry could never match. American factories produced 49,324 Sherman tanks during the war, more than all German tank production of all types combined. British Commonwealth forces received thousands through Lend-Lease. The Soviet Union received over 4,000 diesel variants. Every theatre where Sherman served confirmed what Kummersdorf testing had revealed. Properly maintained, Shermans kept running under conditions that would disable or destroy German tanks. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German tank crews who captured and used Shermans universally praised their automotive excellence in letters, reports, and post-war interviews. Reports from the Eastern Front noted that German mechanics found even the complex Chrysler, a 57 multi-bank engine with its 5 separate engine blocks, easier to troubleshoot compared to German tank engines that required specialized knowledge and equipment. The Ford GAA V8, praised by Allied crews for its exceptional reliability and power output, seemed remarkably dependable to German mechanics accustomed to Maybach engines that required constant adjustment of valve clearances, ignition timing, and carburetor settings. The General Motors twin diesel, which the US Army had rejected as less reliable than gasoline engines and relegated to Lend-Lease production, far exceeded the performance and reliability of any diesel engine German industry had produced for tank applications. This hierarchy of reliability was devastating to German engineering pride. What Americans considered their worst option exceeded Germany's best efforts. The technological gap was not merely significant, it was categorical, representing fundamental differences in industrial capability and design philosophy that could not be bridged through incremental improvements. The Sherman's generous design margins provided another advantage that German engineers came to appreciate through testing and analysis. The basic transmission and final drive components, originally specified for the 30-ton M4 with 400 horsepower, required no major modification to handle the 42-ton M4A3E2 jumbo assault tank with its significantly increased armor protection. The same components that powered the standard Sherman successfully transmitted 650 horsepower from experimental engines without failure or need for reinforcement. German engineers tended to calculate that such overbuilding represented waste, excess capacity, that increased production cost and used scarce materials without immediate benefit. American engineers understood that margins provided growth potential for future upgrades and battlefield reliability that made the extra investment worthwhile over the vehicle's service life. This philosophical difference between optimal design and robust design determined whether vehicles could be upgraded and whether they survived the inevitable abuse of combat operations. By summer 1944, German tank commanders facing the Allied invasion in Normandy knew their technical disadvantages extended far beyond individual tank capabilities. American artillery superiority, devastating close air support, and overwhelming logistical capacity combined to overwhelm German forces, regardless of tank specifications or tactical prowess. But the Sherman's reliability meant American armored units could sustain continuous operations that German panzer divisions simply could not match. American tank battalions could launch attacks, sustain combat operations, conduct pursuits, and immediately prepare for the next operation without extensive maintenance halts. German panzer divisions had to carefully husband their limited operational vehicles, calculating that every movement consumed precious remaining component life and brought mechanical failure closer. The difference in operational availability determined which force could maintain offensive pressure and which had to carefully ration its limited combat power. German use of captured Shermans in combat operations provided final proof of American automotive superiority from the German perspective. The 150th Panzer Brigade, formed specifically for infiltration operations during the Battle of the Bulge in December 1944, attempted to obtain captured American vehicles to disguise their operations. German planners wanted Shermans specifically because of their reputation for reliability. However, the brigade received only 2 Sherman tanks, and only one proved serviceable enough for operations. The serviceable Sherman never actually saw combat due to massive traffic jams that prevented the infiltration operation from achieving its objectives. But the fact that German special operations planners specifically requested Shermans for a mission requiring vehicles to function without breakdowns, while operating behind enemy lines far from any support, demonstrated what German military professionals understood about comparative reliability. Only American equipment offered reasonable chances of sustained performance such missions required. German tanks, even when fully operational, could not guarantee the sustained performance that critical operations demanded. January 23, 1945 brought the final official admission of German automotive failure. A meeting of the Panzer Commission produced a report documenting catastrophic final drive failures across all German tank types. The document's findings were devastating. Prior to the 1945 Eastern Offensive, there were 500 defective final drives in the Panzer IV, 370 in the Panther, and roughly 100 in the Tiger. Additionally, approximately 200 failures had been reported in the Hetzer tank destroyer, based on the Czech 38-ton chassis. General Wolfgang Thomale, General Lieutenant and Chief of Staff of the Inspector General of Panzer Troops serving under Guderian, explained the operational impact in stark terms. In such circumstances, orderly utilization of tanks was simply impossible. The troops lost confidence in their vehicles, and in some situations abandoned whole vehicles just because of final drive problems, fearing they would be stranded and captured. German tanks, built to intimidate through impressive technical specifications, failed in the most fundamental requirement of armored vehicles: mechanical reliability sufficient to reach the battlefield and complete missions. Kummersdorf testing facility prepared for evacuation in early 1945, as Soviet forces advanced relentlessly toward Berlin. Engineers frantically packed testing data and shipped documentation to facilities farther west, hoping to preserve technical intelligence for post-war analysis. Some of the captured tanks, including at least 2 Shermans, were pressed into improvised service with combat units desperately defending the approaches to Berlin. These vehicles fought alongside German designs in the final desperate battles, providing one last comparison under actual combat conditions. The Shermans continued operating until destroyed by enemy fire or abandoned when fuel supplies ran out. The German tanks, including Panthers and the few remaining Tigers, broke down from mechanical failures at rates that shocked even experienced crews accustomed to poor reliability. The contrast remained stark even in the war's final days. American machinery designed for reliability continued functioning. German machinery designed for performance continued failing. The story of the captured Shermans, tested at Kummersdorf, represents one of the great industrial disparities of World War II. German engineers working within an industrial system that prioritized theoretical perfection over practical utility produced tanks that looked impressive on paper but failed in sustained field operations. American engineers, applying decades of automotive manufacturing experience to military requirements, produced tanks that lacked technical sophistication in many areas, but worked reliably under conditions that defeated German equipment. In armored warfare, as in most military operations, the weapon that functions when needed beats the weapon that might be theoretically superior if it could reach the battlefield and complete its mission. Post-war analysis by American and British intelligence organizations confirmed what German testing at Kummersdorf had revealed. Systematic examination of destroyed German tanks found mechanical failures as common as combat damage as causes of loss. Final drives broken from stress, transmissions seized from inadequate lubrication or operator error, engines burned out from overheating or oil starvation. The German obsession with individual vehicle superiority and impressive specifications had blinded them to the critical importance of reliability and maintainability. They built tanks that no conscript mechanic could maintain without extensive specialized training, powered by engines that demanded constant expert attention from skilled technicians, supported by a logistics system that collapsed under the accumulated strain of supplying countless unique parts to scattered units. The lessons learned through testing at Kummersdorf directly influenced German tank design thinking in the post-war Bundeswehr of West Germany. When the Federal Republic began developing the Leopard 1 main battle tank in the 1950s, designers consciously emphasized reliability and maintainability over pure performance specifications. They studied American automotive engineering principles and deliberately applied them to military vehicle development. The resulting Leopard 1 tank incorporated many design philosophies that had made the Sherman successful. Robust powertrain with substantial design margins, easy maintenance requiring minimal specialized tools, standardized components enabling rapid field repairs, growth potential allowing future upgrades without complete redesign. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies and remaining in production for decades. Its success vindicated the American design philosophy that German engineers had discovered through testing captured Shermans at Kummersdorf. The captured Shermans, including War Daddy II with its distinctive name still painted on the hull, represented far more than enemy equipment brought home for technical examination. They were tangible proof that industrial maturity and sound engineering principles based on practical experience mattered more than theoretical technical innovation, pursued without regard to manufacturing reality. German tank designers pursued advanced specifications because they believed superior technology could overcome material disadvantages and numerical inferiority. They were wrong. American tank designers built reliable vehicles because they understood through hard experience that logistics, maintenance capability, and sustained operational availability determined victory in modern mechanized warfare. They were right, and their approach proved decisive. The reliability gap between Sherman and German tanks influenced not just tactical armored warfare, but fundamentally shaped broader understanding of military-industrial capacity and its decisive role in modern conflict. The mathematics were simple and brutally clear when examined objectively. A Sherman with a 75mm gun that reliably reached the battlefield and fought effectively was infinitely more valuable than a Panther with a superior gun that broke down before engaging the enemy, or required 3 days of maintenance for every day of operations. A tank battalion with 80% of its vehicles operational could execute missions that a battalion with 40% operational vehicles simply could not attempt. Reliability was not just a convenience factor or secondary consideration. It was the foundation of operational effectiveness, determining whether armored units could execute their assigned missions. German tanks consistently failed this fundamental test throughout the war. American tanks consistently passed it. Kummersdorf testing had proven this beyond any reasonable doubt by mid-1943, even as German commanders continued deploying Panthers and Tigers that looked fearsome and possessed impressive specifications, but could not be relied upon to function when needed most. The Sherman tank did not win World War II through technical superiority in firepower or armor protection. It won through industrial superiority expressed as mechanical reliability, consistent availability, and ease of maintenance. German engineers at Kummersdorf understood this by mid-1943 based on their exhaustive testing. They wrote detailed reports documenting their findings. They tested the evidence repeatedly with scientific rigor. They reached the correct conclusions about American advantages, but understanding a problem and solving it are fundamentally different challenges. German industry lacked the capacity to retool production around reliability principles, while simultaneously fighting a losing war on multiple fronts against enemies with superior resources. American industry had built reliability into its civilian automotive sector over decades of commercial competition, and simply extended those mature principles to military production with remarkable success. The Sherman's synchronized transmission, that single component which allowed ordinary soldiers to shift gears as easily as driving a civilian car, symbolized everything German industry could not achieve. It represented decades of automotive manufacturing experience, mass production expertise, and design philosophy that prioritized practical functionality over theoretical optimization. Every time a Sherman driver shifted gears without double clutching, without careful rev matching, without specialized technique, the tank demonstrated American industrial superiority. Every kilometer a Sherman transmission operated without adjustment or repair was evidence that German engineering had taken a fundamentally wrong path. Every comparison between Sherman and Panther reliability proved that Americans had solved problems German engineers did not realize they needed to solve until it was too late. War Daddy II, that single Sherman tank captured in Tunisia and tested exhaustively at Kummersdorf for months, told the entire story through its mechanical reliability and consistent performance. Every kilometer it drove without failure was proof that simple, robust design beats complex, optimized design under combat conditions. Every test that demonstrated smooth gear shifting without specialist technique was evidence that accommodating human limitations produces better results than demanding perfection. Every comparison with German transmissions proved that decades of civilian automotive experience created military advantages that could not be matched through theoretical knowledge alone. The tank itself was unremarkable in many ways, just one of 49,000 produced. What it represented was devastating to German confidence, proof that Germany had already lost the industrial war even as fighting continued, proof that American productive capacity could not be matched regardless of German technical sophistication or tactical skill, proof that in modern mechanized warfare, the ability to keep vehicles running matters more than the ability to make them technically impressive. The transmission that German engineers examined so carefully at Kummersdorf embodied this truth in every synchronized gear, every helical cut tooth, every component designed with generous margins and practical functionality. It was not the most efficient transmission that could be designed. It was not the most theoretically optimal solution to power transmission. It was simply a transmission that worked, consistently and reliably, operated by ordinary soldiers under terrible conditions, maintained by mechanics with basic tools and limited training. That practical, unglamorous reliability won the war more surely than any technical sophistication or engineering brilliance could have achieved. The German engineers at Kummersdorf understood this. Their reports documented it clearly, but understanding came too late to matter. The war was already decided by industrial capacity and automotive reliability before the first Panther rolled off the production line. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.